Mm, Anyone? Can you see the screen?
Yes, sir.
Okay, thank you. So I am Harish, uh, 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 PMRF student at ISER Mohali, and as you all know that we are here for the live interaction session for the course Introduction to Rings and Modules. So it's going to be our second interaction session, and we are just going to discuss some of the problems related to the content that is covered in this week 2. So if you have any doubt in any of the notes in week 2, then you can ask me. Otherwise, we will start with the problems. Okay, so I hope that you all understood the definition of an ideal. So let me just start with some examples related to the ideals. So for the first question, let's say if U is an ideal of a ring R, and this is a ring, a commutative ring with unity. Okay. Uh, anyway, in our course, we by ring also we just mean a commutative ring with unity. So no need to uh, again specify the commutative and unit part. So let us define this set R of U for this ideal, and this is the set of all elements in the ring R such that XU is equal to 0 for all X belongs to R. Okay, sorry, for all X belongs to U. Then this set has an important property that it also turns out that this set is also a unit. So
For all U in U.
So it is the set of all elements in the ring R such that when you multiply elements of U with this X, they got vanished. So XU is equal to 0 for all X in U. U is an ideal. Is it clear? So one can show that this new set RU is also an ideal of the original ring R. So you already have an ideal. Using that, you can define another ideal, and this new ideal plays a very important role when you go and you will read modules. Then
Please check the definition of R of U.
I think it's okay, no problem. This is just a set. We already have an ideal and we are defining another set. So what do you think? It's not an ideal?
For all U in U or for all X in U?
Oh, yes. Yes, you're right. There is a yes. This is for all U in U. Yes, I was saying right, but I just wrote it incorrectly. So it's the set of elements that on multiplying uh, gives you 0 with any element of the capital U. Yeah. So can you see that it's an ideal? Anyone?
First, let us prove it is non-empty.
Yeah. So for non-empty, what elements you have in mind? The first element?
0.
Yes, 0 is there. Good. 0 belongs to R of U, and that implies that R of U is a non-empty set. Good. The second thing is, of course, to check that R of U forms an abelian group. Is it just, you can just say that it's a subgroup of, additive subgroup of the ring R. So can you, can anyone just say something about it? So how we are going to check whether something is a subgroup or not? This is easy, right? You just pick some element X and Y in this R of U. It will give you that XU is equal to 0 for all U in U, and Y of U is equal to 0 for all U in U. And that will imply that when you multiply X minus U with U, as the original elements are from the ring, so this you can distribute them like this, and as X of U and Y of U are both 0, so they turn out to, it turns out that on multiply with X minus Y also you will get 0. That holds for all elements of U, and thus X minus Y is also inside R of U. So it's an additive subgroup of R. Now the third property, let R is an element of the ring, and you have some element of the set R of U. Then if X belongs to R of U, that clearly implies that again X of U is equal to 0 for all X belongs to U. But that will imply that when you take R X dot U, that is nothing but R of 0, and that is 0, and that holds for all U belongs to U. Okay, so definitely here one can say that this is this R of U is an ideal of R. Yeah, so a question which is not directly related to this course, but it's good to see that what happens when we have the non-commutative ring. So one can check that even if you have a non-commutative ring, then you can define ideals, the left side ideal and the right side ideal. And it turns out that this set is a two-sided ideal, even if the ring is not commutative. So left side ideal, similarly, you can say that X belongs to the set, and if for any R in the ring, Rx belongs to the set, then you say, and of course additive subgroup part is there, then you say that the set is a left ideal, and instead of checking Rx belongs to the set, if you check that whether X dot R is inside the set or not, then that property says that the ideal is a right ideal. And if it is a left and right both, then we say that it's two-sided ideal. So when we are in commutative setup, then definitely left and right has the same meaning, because Rx is same as your x of R. So we are not caring with that. But why I am highlighting this? Because this ideal is very important when you go and read the module theory. There is something called annihilator of an set or annihilator of an ideal, and there definitely there are modules which are defined on the non-commutative setup, and then you have to check that whether this turns out to be an ideal or not. So actually, if you are in already have an ideal and you define another set, then that this set is always turns out to be a two-sided ideal. Okay. I hope this is clear. Any doubts or any comments from anyone? All good till now? Okay. If that's the case, then let's see some other examples of ideal. So we just write question number 2. So again, we are taking that U is already an ideal. So U is an ideal of a ring R, and we are defining some other set, say R of U, RU, as the set of all elements inside R such that is Rx belongs to U for every small r inside the ring R. Okay. So this time we are not supposed to equate it to 0, but even if it is belonging inside U, then it's also fine. And now we are varying all elements over the ring R. So yes, so it turns out that this set is also an ideal. Prove that R U is also an ideal of R, and it contains U. Okay, so if you are already given an ideal, then you can construct another ideal which contains that ideal. Okay, so this ideal may or may not be equal to the whole ring R, but it definitely contains this ideal. So is this the question is clear? The definition of RU? So maybe we can start with the easy part. So can anyone just say why it contains U? Muthu, you have already spoken, so maybe someone else. Any comment? Why this set contains U? Whether elements of U satisfies this the property listed here?
It contains U because U is an ideal.
Yes. So it trivially satisfy this property, right? All elements of U trivially satisfy this property. So just by the property of ideal, you already know that if U is inside U and X is inside the ring R, then uh, R of X, which is just uh, okay.
Better we can use small r in capital R.
Yeah, just to highlight, this element is from U. I am using small u. So XU is same as UX because you are in commutative setup. So and by the definition of this, XU is always inside U when your element is U is inside the capital U. So this implies that U is contained inside this set RU. So it definitely contains the ideal U. And the second thing is to check whether it's an additive group or not. So it's not going to be empty. That's clear from this observation itself that it contains another ideal. But whether it's an ideal in itself, that's the question that we are going to see next. So for additive group, let's say there are X and Y inside RU. What it will imply? It will just imply that RX and RY, they are inside your U for all small r in the ring R, and that will imply that Rx minus Y, that is Rx minus Ry, will be inside the U because U is already an ideal, so it's closed under this A minus B thing. So that's why Rx is there, Ry is there, so Rx minus Ry is already there. So here is the point that we are using the properties of the ideal. So we cannot define this set for an uh, arbitrary set. We need an ideal in the background, and using that we can define the new ideal. So thus one can say that X minus Y, and as this also holds for all R inside the ring R. So this implies that X minus Y is there in the original set in consideration. So it forms an additive group. Now, second thing is to check that whether it satisfies the second property of the ideal. So let's say some maybe S we can take. S belongs to the ring R and X belongs to this set R of U. So what your take on that? Whether Sx will be there inside the set Ru or not. So this implies that Rx belongs to U for all R in the ring R, and as your S is already there in the ring, so we need to check that for this element Sx, we have Rs of X inside the U or not. So Rsx is same as Rs times X, right? So this is inside the ring because R is there and S is there, and X is already there inside R of U. So you have that for all R in R, Rx is there the inside you. So just replace R by this Rs. So using this, you can say that Rsx is already also there inside you for all S in R. And thus it gives you that Sx is already also there in Ru. And it thus you get that it's also an ideal of the ring R. So we saw that these two are some ideals that you can get from an already given ideal. So now let us define something that elementary means you have an element of the ring R, then how can you get an ideal containing that element? So the third question is regarding that only. And so third question is, and this the ideal that I'm going to define in this question is used in proving that the all a ring is a field if and all a commutative ring with unity is a field if and only if it has just two ideals, the trivial ideal and the ring itself. So so this ideal that we are going to define, so this is used somewhere in the proof of that. So if you are following the notes, then you already know that how to prove the statement. So let R is a ring and A is an element of the ring. Then one has to show that this set AR, which is this set is also sometimes people say that it's a ideal generated by the element A. So this set is an ideal of R. Okay, and somehow after proving this, you can appreciate that why we need R to be commutative, because this is not going to be a two-sided ideal when the ring is not commutative. And I will show you through an example that if you are not considering R to be a commutative ring, then this is not going to be a two-sided ideal. So, but let's first see that it's an ideal if we are in our current setup of commutative rings. So this is also easy to see, not a problem. So definitely, as one is inside R, so therefore A dot one, that is A is inside your A of R. So this implies that this set is not going to be empty set, and if say X, Y belongs to this set AR, then as per the definition of this set, X is going to be some A times R1 and Y is going to be some A times R2 for some R1 and R2 inside the ring. And thus, what is X minus Y? This is just A R1 minus A R2. You can just take A to be common, R1 minus R2, and it's again going to be inside the set A of R. So it's closed and under the operation A minus B. If X is there, Y is there, then X minus Y is also there. So thus it forms an additive subgroup. Now one has to check that whether it's a ideal or not. So one more thing we have to check, that with multiplication by the elements of ring, whether it is closed or not. So let's say that let R is inside the ring and X is any element of this set. Then what can you say about Rx? So one is, so as X belongs to AR, we have X is equal to AR1 for some R1 inside R, and to check that whether Rx is there or not, we have that Rx is equal to R1, oh, not R1, it's AR1, and as the ring is commutative, we can just write it as ARR1, and this part is there inside the ring, and thus this belongs to A of R. So thus this turns out to be an ideal of R. Okay, so sometimes people used to say that this ideal is the ideal generated by the ring generated by the element A, because this is the smallest ideal that contains A. If you take any other ideal that contains A, then this ideal has to be a subset of that ideal. So that's why this is said to be the ideal generated by this element A. So when you are in commutative setup, then this kind of things you can do. This is always an ideal. But if you are not in commutative setup, then this is not going to be a two-sided ideal. And let's see an example so that you can appreciate why we have in the beginning assumed that the rings are commutative rings with unity. So this is just as a caution I am going to write AR is not a, so if you are in commutative setup, then this word has you can definitely omit this word two-sided, because any ideal is two-sided. But if you're not in commutative setup, then you have to use this word. So it's not a two-sided ideal if we have R to be a non-commutative ring. So what's an obvious example of a non-commutative ring? What's the first example that comes to your mind? Any any non-commutative ring?
Matrix multiplication.
Yeah, matrix with usual multiplication and addition. Yes. So let me just okay. So let's just see an example from the matrix ring, because this is the first ring that comes to our mind when we try to think of a non-commutative ring. So R is, you can take to be just matrix ring over integers, such that A, B, C, and D all are integers. And so for defining A of R, you need an element A. So I'm choosing an element A as this matrix. So 1, 1, 0, 0. So definitely this is inside your ring R. So what is your AR then? AR is going to be the elements in the of this form, A times the element of the ring, right? But what is this set? This, you just multiply these two matrices, you will get that this is going to be doing something. Shows this will give you a plus c, right? To multiplying this, and here you will have b plus d, and this is 0, this is 0, right? Where a, b, c, d are all integers. Agree? So this is the set AR, and to check that it's actually not an ideal, one has to say that it's not so closed under addition, or it's not closed under multiplication with the ring element. So additive subgroup, you can easily see that it's going to be an additive subgroup, but it's not going to be closed under multiplication with the elements of the ring. So if you pick an element like this, that R is the element with 1 at each coordinate, then you can see that there is R times X. What is and this so this is an element from the ring. You have to pick an element from this set also. So A belongs to AR, right? You can just take this to be identity, ABCD to be an identity matrix. When you multiply this with an identity matrix, you are going to get it again. So A belongs to AR, but what about their multiplication? R of A. So R of A is 1, 1, 1, 1, and it's 1, 1, 0, 0, right? So what is going to be 1, and then 1, 1, and 1. So it's again coming out to be R, but that is not inside A of R, right? Because for in the set A of R, the second row is 0, 0 row. You can see that in the definition of AR, the second row is 0, so it's not inside AR, right? So it's not closed. This set is not closed under multiplication with the elements of the ring. So this implies that AR is not left ideal. Okay, so it's not definitely not going to be a two-sided ideal because it's not a left ideal. So that's why we in the beginning of the course, in the last lecture, I said that we are considering the rings with unity and rings with that are commutative, because that allows you to build up some nice results, some nice theories. So I think now you all can appreciate this. Yes. So is there any doubt in this question or in this observation, or shall we move ahead? Okay. So if there are no doubts, so let me just try to write a new another question. So now we have constructed rings, sorry, ideals from an already given ideal. So now next question will definitely, I think, give you more idea about the ring operations in rings, and you will see that a ring you can be made isomorphic to another ring which has the multiplicative identity to be the 0 element of the initial ring. So that's something interesting that we are going to do. So let's say that you're all given a ring R. So given a ring R, then using we can the elements of the ring, we can define another ring. So we can define another ring, say R tilde, using the elements of R in the following way. So what I mean by this phrase, using elements of the ring, are that as a set, R and R delta are going to be same. So so I am having the same set. I'm just going to change the operations. As a set, R delta is same as R. Okay. And you will see that even after altering the group operations significantly, I'm going to get back this R in R delta is going to be isomorphic to this R. So let me just define the new operations. So let's say R has operations, this had operations plus and dot. Okay. So I will define new operations like this: A addition with B. So A, B are elements in R as well as R delta because they are already same as the sets. So this new addition is defined from the addition of this ring R in this way, and multiplication we are going to define is like this: AB plus A plus B. So this AB is multiplied by the laws of this ring R, and the addition is definitely also by the laws of this ring R. And we have this plus circled plus and this new product as being defined using the operations of this ring R, and we see that this turns out to be a ring in itself. So we are defining it for all AB belongs to R. Okay, so here on the left hand side, the addition left hand side, the addition and multiplication are from the ring R, and on the right hand side we are defining new operations for our ring R delta. So we proved that before saying that it's a ring. So yeah, first thing is to check that whether it's a ring or not. Okay, so prove that first thing R tilde with this new addition and multiplication, this algebraic structure is actually a ring. And again, by ring I mean a commutative ring with unity. So we will also see that. Now second proper thing, one has to show that R and R delta are isomorphic.
Elements of R delta are the same as the elements of R?
Yes. Only the operation we are changing.
So that we'll have to mention.
Yeah, I said na ki, another ring R delta using the elements of R. As I said, R tilde and R are same. Okay. Yes. So maybe you can just stare at the question one so that you understand what is happening. So we already have a ring with some addition and multiplication. Then using that ring, we are defining another ring with an entirely different notion of addition and multiplication. And then we are claiming that these rings are going to be same, like up to isomorphism. And you will be surprised to see what are going to be the additive and the multiplicative identity for this new uh, uh, ring that we are defining. Okay. So is there any doubt on the definition? No. So if no, then let's try to prove that it's actually a ring. Solution. Claim. First claim is to prove that this set, which is same as R, this with the newly defined addition is an abelian group. So we can't use the trick that A is there, B is there, then A minus B is there, because the group operations are now different from R and R delta. So we have to define, we have to check independently all properties of the group, and that will give you some idea of how this operation is going to change the elements of the ring R. Okay, so it's somehow permuting the elements of R in such a way then that the new operations are actually giving again the ring structure, and both algebraic structures are same as rings. Okay, so let's check it once. So closure, I don't think any doubt should be there for the closure, because what is A plus B in this setup? This is going to be A plus B in the old setup plus 1. And since A is there, B is there in the ring, and 1 is also there. So this is always going to be inside R delta, right? Because as an elements, R and R delta has the same, are defined on the same set, right? So and they have the same elements. So A is there, B is there, 1 is there in the original ring. So definitely A plus B plus 1 is also there. And this follows because of the closure property of the original ring, right? Because here the additions are with respect to the addition in the original ring. So due to the addition is closer in the original ring, that's why this expression A plus B plus 1 is going to be inside this ring R delta. Okay, any doubt? The silence, with silence, I assume that everything is going clear. If at any case, any stage you have any doubt, then feel free to ask the questions. Okay, so associativity. A addition with B, and then I am adding it to C. So can anyone just help me step by step? What's going to be the A plus B? It's going to be A plus B plus 1, right? And then you are adding it with C. So now this is your first element. and this is your second element. And this operation is what it is doing. It is adding the first element with the second element with the previous law, and then adding 1 to the final outcome. So what it will become? It will just become a plus b plus 1. The first element is there, and this, then c, then 1. Okay, so it's going to be a plus c, oh sorry, a plus b plus c plus 2, because the already given operation is abelian, so you can just uh, go from here and there, and this is what you are going to get. So this is one side of the associativity part. Second side is this a plus b plus c. So what is this expression turns out to be? A is going to be added with the product with the outcome of b and c. So it's b plus c plus 1, and then by the definition you have to add the first element with the second element, that is b plus c plus 1, and that is going to be added to 1. So it is a plus b plus c plus 2 again. So associativity is there. Doesn't matter in how you add these two things, they are always going to be the same, right? So associativity part is also clear. Yeah. Any doubts on that? If not, then maybe we can move to the next part. Yeah. So here something interesting is going to happen. What is the additive identity? Oh. Additive identity. Any idea? Any guess?
Minus,
There were two noises parallelly. Yes.
-1.
Okay. And Pradeep, your take? You also said something, na? Is it -1 or something else, Pradeep?
-1, -1.
Oh, okay.
-1.
Okay. Okay. So yes, it's going to be -1. So which is so we are talking about the additive identity. So it's just the additive inverse of the multiplicative identity of the original ring structure, right? So for additive identity, we just want to see that, okay, it should have this property: A addition with B is equal to A, and that is B addition with A for all A in R tilde, if B plays the role of additive identity. But that is same as A plus B plus 1, and you are equating it to A. So that will imply that B plus 1 is 0, and thus you get B to be minus of 1. So just by altering the ring operation a bit, the additive inverse of your multiplicative identity have now become the additive identity for the new ring structure that we have defined. Okay, so yeah, now let's see what is the additive inverse. So additive inverse, let A belongs to the set A delta. So for additive inverse, you want A plus B to be the identity of this A tilde. Oh, addition is also with respect to this new ring structure. And identity here is -1. So A plus B is A plus B plus 1, that is minus of 1. Yes. So this implies that your B is -2 minus A. And A is already there inside the ring. Minus A is also going to be there. And 1 is there, so -2 is also there. Thus, this element belongs to the set R. Thus, it also belongs to the set R tilde. So we have additive inverse for each element inside this R delta. So this implies that your structure is at least a group. Okay. So now we will check that whether it's an abelian group or not. So, abelian.
Change the operation. Or delta.
Yes. Thank you, Muthu. So abelian property one has to check. And that also not difficult to check because we have additive commutativity in the original ring. So we can just write A plus B as B plus A plus 1, and that is same as B addition with A, right? So abelian part is also there. So this is not just a group, but it's an abelian group. So at least the group structure is there. Okay. So now let us see whether it's a commutative ring with unity or not. So for that, another property that we have to check is the closure under the multiplication that we have defined in the beginning, and that will also follow from the closure property of the initial ring. So what is the multiplication that we defined? It was just AB plus A plus B, and it belongs to R delta due to the closure properties. So we are using it closure property for the initial ring, the closure for both addition and multiplication. So because A is there, B is there, then AB is definitely there inside the original ring. So due to the closure property of R, this follows, right? Now, associativity with respect to the multiplication that we have to check. So multiplication is associative. So till now, I think everything is okay. If you have any doubt, then just let me know. Okay. So what we are doing, we are multiplying A plus A with B, and then we will multiply it with C. So what we are going to get here, so this is AB plus A plus B, and we are going to multiply it with C. So how this operation is defined, we just take the multiplication of the first element with the second element. So AB plus A plus B C, then add the first element and then add the second element. Okay. And now we can use the distributivity of the original ring operation. So it's ABC plus AC plus BC plus ABC plus, oh, sorry. This is AB plus A plus B plus C. So this is what we will get if we are multiplying the outcome of the product of AB with C. Now, on the other side, let's just multiply the outcome of B and B product C with A. So A product B times C. So what is B times C in the new multiplication? This is BC plus B plus C. So now use the definition of multiplication again. So just multiply the first element with the second element, that is A times BC plus B plus C, and then add the first element and then uh, add the second element. Okay, so what is going to be? It's going to be ABC plus AB plus AC plus A plus BC plus B plus C. And this is definitely uh, commutative with respect to addition. So you can say that this is same as ABC plus AC plus BC plus AB plus A plus B plus C, right? So both these things are same. So the associativity with respect to the multiplication is also there, right? Okay. So I hope this is clear. Associativity is also there with respect to multiplication. Okay, so now we can search for the multiplicative identity. So what your guess, although I said it in the beginning of this question, but can you guess it from the calculations that what is going to be the additive identity? Oh, sorry, multiplicative identity?
0.
Yes, 0. Good. So Muthu, you also think it to be 0? I think it is Pradeep, right? Good.
Identity
Pradeep.
is
Sir,
zero.
So it's
sir,
going to,
Pradeep.
okay. So that's going to be 0. Good. So we'll just see how it is coming out to be 0. So for multiplicative identity, what you need, that A multiplied with A is going to be A again, and that is same as 1 multiplied with A, and that should happen for uh, I should not write 1 here because that's a notation for the unit in the original ring. So I will just write maybe 1 R tilde. I hope that notation is okay. So that should happen for all elements in R tilde, right? So, but what is this? This is just A dot 1 plus A plus 1, which is A plus 1, right? And we are expecting it, so that is so there is just some notational mistake I did. So I should write again it as A dot 1 of R tilde plus A plus 1 of R tilde, and that is going to be same as A. So this will implies that A in addition with 1 of R tilde, sorry, multiplication 1 of R tilde in the ring R, that is going to be A plus A plus 1 of R tilde is equal to A. If I'm not making any mistake. Let's check it. Yeah. So, sorry. What it is? So you can just cancel this A with this A, right? Oh, there is also one mistake. So we cannot write A dot 1 of R tilde to be A again because it's not a multiplicative identity in R. So this is A dot 1 of R tilde plus 1 of R tilde. That should be 0 in R, right? For all A in R tilde. So beware of the notations here. So are you guys able to follow? So what we are doing, we just want an element inside the ring R delta such that on multiplying it with every element of R delta, we are getting it the element back. That is the definition of multiplicative identity. So we want A multiplied with 1 of R delta. So I'm just denoting the, we have to find what is this 1 of R delta. But if there is just some element of this which acts as multiplicative identity, then it has to satisfy this. So A multiplied with 1 of R tilde is same as A dot 1 R tilde plus 1 plus 1 of, plus A plus 1 of R tilde. And that is going to be same as A due to this relation. So now this addition is happening, additional multiplication here is happening inside the original ring R. So we can just cancel this A with A. So we are left with A dot 1 of R tilde plus 1 of R tilde equal to 0 of R, because A is already cancelled here. The addition is in the ring R, original ring. So we can write the 0 of R. I'm not writing 0 because that will create a confusion. So it's an additive identity of R. Okay. Now, and as I said earlier, we cannot just multiply A with 1 of R tilde and say that it's A, because it's not 1 of R. It's something that we don't know yet. We have to find. So that's why I did the mistake in the earlier calculation. So this has to be remained as it is. So till now, it's is it okay? Maybe you can just stare it for a moment, because there are some notational things that are happening and you might be new with these things. So you can just stare it for a moment, and if there is anything doubt, then you can just ask me. All good till now? Okay. So what we can do, we can just, some people, I think someone has just switch on his mic. Okay. So so what you can do, you can just take this 1 tilde out, because this is as distributive in the original ring, or let's say you can write it as 1 of R times 1 of R tilde first, So what I did, see, this is an element in the original ring as well. And we have multiplicative identity in the original ring. So that multiplicative identity with multiplied with any element is going to give you back the element again. So I can write 1 of r tilde as 1 of r dot 1 of r tilde, because here the multiplication is, this multiplication is in the original ring R. So this step is clear. I'm just writing an element A as 1 dot A. Okay, that I can do. So now you can take this R of 1 of R delta outside, right? Because the, let me just write the explanation also here, so that if you see the notes, you won't get confused. So I'm doing this because 1 of R is the multiplicative identity.
What is that IR?
I is 1 of R. 1 of R. Okay. Thanks, Muthu. So this is 1 of R is the multiplicative identity. So this might look tricky for the persons who are looking the ring theory questions for the first time. So please don't hesitate to ask. I'm there to solve your doubts. So ask whenever you find a problem. So because these things are notational and it might confuse you. So don't hesitate to ask. So IR is the multiplicative identity of R. Okay. So that's why we can just multiply this element with our 1 of R and we will get back this element again. Okay. And here I am using the fact that plus and dot are distributive in the original ring R. Okay. Okay. So till now we have this thing, and as this 1 of R tilde is going to play the role for the multiplicative identity. So this thing should happen for every element of R delta, that A plus 1 of R dot 1 of R delta should be the 0 of R. Okay, so this should happen for every element. So it in particular, it should happen for A to be the 0 of R as well. This is also inside R tilde because this is inside R. So this is also inside R delta because as I said, they are same. Okay, so if I choose my A to be this, then what I will get? I will get 0 of R plus 1 of R dot 1 of R tilde to be 0 of R, right? So 0 adding with any element of the ring, original ring, is going to give you back that element, because here the addition is with respect to this uh, the original ring operation. So here for this we have the explanation that, as I said, R and R tilde are same. This S is looking like a D. And 0 R is the additive identity of the ring R. Thus, 0 R must be there inside R tilde as well. Okay, and for so we have 0r plus 1r dot 1 of r tilde is equal to 0 of r. Now 0r plus 1r is going to be 1r. This is because 0r is the additive identity of the original ring structure. Additive identity of this ring structure R plus and dot. So that's why it added to any element will again give you back the element itself. Now this 1R is the multiplicative identity of the original ring, and 1 of R dash is there in the original ring, and dot is the multiplication in the original ring. So what 1 R dot 1 of R delta will give you? Can anyone just say? Except Muthu. Muthu is giving a lot of answers. Good, but someone else. This is easy, right? It will just help me to understand that whether you are getting the concepts or not. So what is 1R dot 1 of R delta? Anyone? If no one, then Muthu, maybe you can just say.
Now for delta.
Ah, yeah, 1 of R delta. Good. Okay. This. So this is going to be 1 of R delta, and this is same as 0 of R. And this is happening because 1 of R is the multiplicative identity of R plus dot, the original ring. Okay, so 1 of R delta is equal to 0 of R. So as we think in the beginning that the multiplicative identity of the new ring structure is going to be the additive identity of the previous ring structure. So isn't it interesting that you have the ever set, you have a ring structure on it, then you somehow change that ring structure and define the new binary operations on the same set such that the identity becomes the multiplicative identity. So 0 is now playing the role of 1 with respect to the new operations. So whatever we did, can we just say that 1 of R is a multiplicative identity of the new ring structure, or still something more has to be done? See, here we said that this should happen for every element of R delta. And then we choose a particular element and get a choice of this additive multiplicative identity. That if this is going to happen for every element, then certainly it's going to happen for this particular chosen element as well. And thus this is a choice. But now we have to actually see that this choice works out for every element, right? So only thing is to show. So
I have doubt, sir.
yes.
If A equal to minus identity R, then every element is multiplied identity, sir.
If A is equal to minus of
Minus
identity,
identity R.
see, that's what I'm saying, that for something to be a multiplicative identity, it should hold for every element of A, every element of the ring. So not just for minus of 1. So for minus of 1, maybe anything you put here will work, but that won't
Yes,
say
sir.
that this is
But identity element is unique.
the identity element is unique. That's true. But
Sir.
identity element satisfies this thing for every element A, not just for a single element A. So you can't just say that I put A equal to -1 and I will get uh, whatever choices I'm getting, that will be the identity. That's why I'm saying that I put here A to be 0 of R, and I got a unique choice for uh, identity. Now I have to check that this unique choice actually works for all choices of A, not just for a particular A. If it fails for even for one choice of A, I can't say that this is going to be the multiplicative identity. Okay. So when you put A equal to -1, you get the choice that anything can be the choice. But when you change your A, you will see that anything won't be the good choice. That's why I put here something that is going to give us a single choice. Now we can check that for this single choice, this will work out for every A. So Pradeep, is it clear?
Yes, sir. Okay, sir. Yes, sir.
Okay. So what you are doing, you said that you put A equal to -1, then this is always satisfied. That is true. But we can't claim that this is an identity just on the basis of one choice. We have to see that this works for every choice of A. So I also choose here one choice of A and saw that if it is going to happen for A equal to 0R, then this element has to be 0 of R. But I need to check that this element actually turns out to be the multiplicative identity. So the job is not yet done. We have to see that, so we have to check that 0 of R is the multiplicative identity. So now at least we have some fixed choice, and let me just say this equation is 1. So we have something to put in this equation 1. Earlier we don't even have a single choice to put here. Now in place of 1 R tilde, we can just put 0 of R and then see that whether this works out or not. And definitely it's going to work out, because A plus, let me just write, from equation 1, A plus 1 of R dot 1 of R tilde is going to be 0 of R. Now in place of 1 of R tilde, we can, sorry, this we have to check. Uh, let me write it from the LHS of equation 1. We have to show that this LHS is actually equal to the RHS of that equation. So in place of 1 of R delta, now you can put 1 of 0 of R. Now these operations are happening inside the ring R, this plus, this dot, everything, and whatever be the element of the ring, if it multiplied with 0, that is going to give you 0, right? So this is equal to 0 of the ring R, and that is what we have the RHS of equation 1. Clear? So now we saw that this particular choice actually works out for all A. So now it will imply that 0 of R is the multiplicative identity of this new ring structure. Maybe I will just say this part again, and so if you still have any doubt, then you can just let me know. So what we did,
I have
we
doubts, sir.
need to, yeah,
First, you are different part A plus B equal to A plus B plus 1. The one is
yeah.
one identity with R.
One is the identity of the original ring.
Sir?
One is the identity of the original ring. You are saying about the definition that we define, right?
Yes, sir.
This definition, na? So that's why I wrote here in the beginning that in the LHS, whatever is happening, it's happening in the original ring. So this one is the identity of the original ring.
Okay, sir. It is one
Okay.
R. That it is denoted by
That is
one R.
1R. 1R.
Okay, sir.
I didn't
Okay.
mention in the beginning because at that time we don't have two candidates for one. Only one uh, identity was there in our calculation. That's why I didn't messed up with the I don't want to messed up with the notations. That's why I just simply write 1 and 1. But here in the beginning, whatever we did, wherever we are writing any numeric number that is inside the R, whether this 1 or this 2, this is 1 and 2 of the R, not R delta. Okay. Okay. Good, Pradeep. So let me just explain this multiplicative identity once again. So we want to find an element which satisfies this condition, and that element is going to be the multiplicative identity. So what this product 1 of R is, this is A dot 1 of R plus A plus 1 of R. So the product is A times B is AB plus A plus B. So this is A times B plus A plus B. That has to be same as A if this 1 of R is a multiplicative identity. So now this A can be cancelled out with this A because the addition is in the original ring, and there we can do the cancellations. So A is cancelled out with this A. So we have A 1 dot R delta plus 1 of R delta. Now there is nothing here in the right hand side. So this is the 0 of here we have the 0 of the original ring. So I'm writing 0 of R, and this should happen for all A in R delta. And someone has to satisfy this. If 1 of R delta has to be an identity, then it should satisfy this relation for all A in R delta. Now, with respect to this multiplication, this dot multiplication, we have 1 of R as the multiplicative identity. So we can write 1 of R delta as 1 of R dot 1 of R delta. And then as the original ring is satisfy the distributive property with respect to this plus and this dot. So we can just take this 1 of R delta outside in the right hand side. And in the bracket, we can just keep 1 of R A plus 1 R dot. Okay. Now, this condition is what we get from the necessary and sufficient condition for an element to be the multiplicative identity. So this condition should hold for every A belongs to R delta if 1 of R delta is the multiplicative identity. Now, for a particular choice of A, what I saw that if I put A to be 0 of R, so 0 of R is going to be R inside R delta, because as I said, R and R delta are same. So, and 0 of R is the additive identity. So it is inside R, and hence it is inside R delta. So for this particular element, what I saw that 1 of R delta has to be 0 of R. Okay. So if that is, if 1 of R delta is the multiplicative identity, then 1 of R delta has to be 0 of R. There is no other choice. That's what we get by this part. So 1 of R delta equal to 0 of R is the only possible choice. Okay. So if something has to be the multiplicative identity, then this is just 0 of R. No other element will satisfy the multiplicative identity thing because of this thing. Then when you put A to be 0 of R, then it's coming out that 1 of R delta has to be 0 of R. Now we have to check that this actually turns out to be the multiplicative identity. So what we did, the condition that we were getting initially, we just put 1 of R delta to be 0 of R, and we saw that this is being satisfied for all elements A. So A is not playing a role here. For this choice of 1 of R delta, we are getting this equation satisfied for all values of A. That's why 0 of R is the multiplicative identity of this. So I could have easily started by saying that, okay, let's prove that the multiplicative identity of 1 of R delta is 0 of R. Then I would have just simply put 0 of R here and showed that, okay, this condition is satisfied for 0 of R, then it's the multiplicative identity. That's it. I did all these things just to tell you that why 0 of R is coming as a choice. Okay, so don't believe in flukes or any uncalculated guesses. We are doing mathematics, so at some guesswork also needs to be explained, that why you are putting that particular choice. Is there anything significant about that? So 0 of R is the obvious choice because if you put A equal to 0 R, then there is no other element which is which you can take it as a choice. Okay, now see, still this part is left. A equal to 1 product A. But if we check that this multiplication is commutative, that we are going to check because we have to show that this R delta is a commutative ring with unity. So if we check that part, then we need not to check the other part of this equation, that A is equal to 1 product A. Because if this multiplication is commutative, then 1 product with A is same as A multiplied with 1. Thus, checking this part is good enough. If we check that this product is a commutative, is commutative. Got it? So what I'm saying, that this part, once we check that this product is commutative, then we can omit this part. Okay, and that's going to be our next agenda, because we have already shown that the ring is closed under multiplication. It satisfies the associative property. It is having the unit. Now the next part is to show that the multiplication is commutative. So till now, do you have any doubts? So the next thing is multiplication is commutative. Okay. So we need to show that A multiplied with B is same as A multiplied with A multiplied with B is same as B multiplied with A. So we want to show that A multiplied with B is same as B multiplied with A. Yes. So do anyone want to comment on that? How we can just say that? So you have this LHS part to be A, B plus A plus B, right? And that is same as BA plus B plus A. And that is going to be this part, right? So this is just coming out due to this follows due to the commutativity of this follows since this operation dot is commutative in your original ring. So if you are not having a commutative ring, then this ring is also not commutative. So, but we are having commutative ring, so multiplication is going to be commutative. Yes. What else? All. So can we say that it's a ring or something else is remaining?
Distributive.
Yes. Thanks, Muthu. So distributive part is still left. We have to show that this is distributive as well. So distributive property. So I have seen it many times that while writing exams or while checking it's a ring or not, students generally forget about this property. But this is also an important property, and some rings don't turns out to be ring just because of this property. So don't forget to check this property, because addition, multiplication, everything people checks because this is in the regular routine. But distributive part, many people just don't remember it at the time of exam. So just keep this in mind and don't forget to check this property also. This is also an important property. And many rings fails out to be rings just because of this property. Okay, so let me just check it for you that this ring is also satisfying the distributive property. So for distributive property, what we need to see that A added with the product of B plus C is same as A plus B. I'm doing something. Let me just check one part. This part I'm going to check. The other distributivity, maybe you can check. So I'm checking that multiplication is distributive over the addition. So what is B plus C? This is B plus C plus 1. And what is A times B plus C plus 1? This is A, B plus C plus 1 plus A, and then plus B plus C plus 1. So this is going to be AB plus AC plus A plus A plus B plus C plus 1. And what is the other part? That A plus B in what added with A multiplied with B added with A multiplied with C. So these two things has to be same. Then you can say that the multiplication is distributive over the addition. So that is same as A B plus A plus B, and one has to add it to AC plus A plus C. And adding is first element, then second element, and then 1. So this is same as AB plus A plus B plus AC plus A plus C, and then you have 1 in the end. And as the ring is commutative with addition, the original ring, so you can just write it AB plus AC plus A plus A plus B plus C plus 1. So these two things are same. So distributive with respect to so multiplication is distributive uh, uh, over the addition. So that we have checked. You can also check that the other thing, you have A plus B. I don't know how to write that. Sorry. A plus B times C, and here you can take what I'm doing. With this part you can leave for the moment.
Or again, is it not multiplication is distributive over addition only?
Yes. That's why I'm just leaving it. So now we can just say that R tilde is a ring with the new operations that we define. Okay, and here by a ring I mean a commutative ring with unity. Okay, so that's the first part of the question. So why I have chosen this large question, long question, because so that you get familiar with the properties of the rings and how you do calculation inside a ring. And one more thing, in the beginning of the course, people just said this in their mind that 0 is our additive identity always, and 1 is always our multiplicative identity. They are just the symbols, the notations. And if you change the group operation, the binary operations, then the as an element, their role might get changed. That's why I define a different binary operations, and then we saw that the 0 of the earlier ring setup was actually turns out to be the 1 of the new setup. So don't uh, get acquainted with the hypothesis that 0 is always a multiplicative identity. It's just a notation for the multiplicative identity. Okay. So I think now you guys are familiar with how to work with the rings. Oh, so so I went to the question for the sake that the second part is still needed to be shown, that R and R delta are isomorphic. So we changed the operations, everything got changed. The additive identity in the earlier setup becomes the multiplicative identity. The -1 of the earlier setup became the 0 of the new setup. But still, as a ring, they are same. They are isomorphic to each other. So we are not losing or gaining anything in that sense. But we are just looking at the elements from a different perspective, from a different ring structure. So that part is also pending. So I will try to show that before that time runs out. So the second part, solution to the second part, we have to see. So our claim is the earlier setup R plus dot is isomorphic to the new setup R tilde plus and this multiplication. And this is a ring homomorphic, the ring isomorphism. Okay. Yes. So for ring isomorphism, first thing we need to show that the identity is mapped to the identity, the multiplicative identity. So first property is phi of first claim. The claim I should write. So claim 1 is phi of Oh, sorry, what I'm doing. So first of all, I have to define an isomorphism, right? So define a map phi from R to R tilde S. So phi of X has to be mapped to somewhere. So can anyone just guess what this map can be? See, we want to make the multiplicative identity of the first element to be the first string to be the multiplicative identity of the second element, and also you have the information that the additive identity has to be mapped to the identity. So you already have these things in background, that for something to be a ring homomorphism, at least you need phi of 0r to be 0 of R delta, and phi of 1R is 1 of R delta. So for ring homomorphism, we need these things. So what is 0 of R delta? That is minus 1 of R, and that this is 0 of R delta, 0 of R. So from these two things, can you guess what we how we should define? Yeah, two people just said something. Maybe one by one, if you can say, then it would be good. Yes. Now no one is saying anything. Yes. Just speak up. Or if you want to write in the chat, then also you can do. But I will prefer the to hear the voice. Whatever you said, just repeat it. No. You have to map, define a map such that 0 is mapped to -1 and 1 is mapped to 0. Yeah.
X minus 1 or
Yes. Good, Pradeep. So one such choice is map any element x to x minus 1. Okay. So using whatever we so this will help us to guess that this we can define x to just x minus 1 of R, right? So now we will check that this is actually a ring isomorphism. So clearly phi of 1R is 1 of 1R minus 1R, that is 0 of R, and which is identity of the new ring structure, and phi of 0R is 0R minus 1 of R, that is minus 1 of R, and which is 0 of R tilde. So these two necessary conditions that we use to define, just guess this homomorphism actually works out. So now we have to just see that for it being a homomorphism, it is compatible with the addition and the multiplication, and then we will see the bijective part. So now claim is phi of x plus y is same as phi of x phi of y. Okay, so this addition is in the new ring setup and this is in the old ring setup. So let us pick the LHS part. So LHS is phi of x plus y, which is nothing but x plus y minus 1 of r. Okay, and the RHS is phi of x plus phi of y, that is phi of sorry, x minus identity of r added with y minus identity of r. So is this part clear? I'm just using the definition of the ring homomorphism, the map that we define. It's not a ring homomorphism yet, but we define the map like that. So now how we define the addition? A plus B is in the original ring A plus B plus 1. Okay, so first element added to the second element, and then we add the 1 of R. Okay, so this is x plus y minus 1 of r, right? 1 minus of 1 of r will get cancelled with plus of 1 of r. So hence the claim is satisfied, right? We have phi of x plus y to be phi of x plus addition in the new ring with phi of y. So this operation is compatible with the addition. Okay, I hope it is clear. Just see, stare it for a moment. If any step is not clear, just let me know. Okay, so if it is clear, then let's move to the next claim, that phi of x dot y is phi of x dot phi of y. So what is LHS? LHS is phi of xy, which is just xy minus identity of r. Okay, by the definition of this phi, what is RHS? RHS is phi x multiplied with phi of y. Yeah, what is phi of x? This is x minus IR times y minus IR, and that is, by the definition of the multiplication, A times B is AB plus A plus B. So A is 1 x minus IR, B is y minus IR, so AB plus A is x minus IR plus B, y minus IR. Just open the first bracket. So here this multiplication is with the original ring, so we can just open it directly. So we have xy minus identity of r dot y minus x dot identity of r plus identity of r dot identity of r. This is through the first bracket we got, and then we have x minus identity of r plus y minus identity of R. So now this 1 of R is a multiplicative identity with this with respect to this dot operation. So we can just write xy minus 1r dot y is just y, and this is x. 1r dot 1r is 1r, and plus x minus 1r plus y minus 1r. So cancel this x with this x and this y with this y. So what we get xy this 1r also you can cancel 1r with minus of 1r. Finally is xy minus 1r, so which is same as the LHS part. So this is also compatible with the multiplication. Okay, so this implies that phi of xy is same as phi of x times phi of y. Okay, just have a look at it. If is there any doubt, then let me know. Okay, I assume there is no doubt. So till now we just showed that phi is a ring homomorphism. Okay, now we have to show that it is also 1, 1 and on 2. So can anyone just say why it is 1, 1? Anyone?
Let pi x equal to pi y.
Okay, let me just follow you, Muthu. So let phi x is equal to phi y for some x comma y in R. Okay, then this will implies phi of x is x minus 1 and this is y minus 1. You can just cancel out this x and y. So this will implies x is equal to y. And hence phi is 1. Okay. Onto part. Do anyone want to say why phi is on 2?
X in R delta.
Yes. For every x in R delta, there exists what element?
X plus 1. 1
Yes,
R.
x plus 1 R in belongs to R such that phi of x plus 1 R is x plus 1 R minus 1 of 1 R x plus 0 R, that is x. Okay, so this implies that phi is also onto, and thus phi is an isomorphism. Okay, so I hope you enjoyed this exercise. So what we did, we start with any ring and we just somehow defined new operations on the same set of elements, and the operations were defined in such a way that the additive identity of the new ring operations turns out to be the minus of the multiplicative identity of the original ring operations. So 0 of R tilde is minus 1 of R, and the multiplicative identity of the original ring operation. Sorry. So multiplicative identity of the new ring is just the additive identity of the original ring. So and interestingly, both the structures doesn't differ because we prove that both structures are isomorphic as ring. Okay, so that's it. Maybe I can just state one more question for you guys to solve as an exercise, and if you have any doubt, then you can just let me know. I don't think I have enough time to say. Maybe let me just write the question, and if I could quickly give you an idea of. Yes, do anyone want to say something? Okay. So, if there is any doubt in the above question, yeah, yes, Pradeep.
Yes, sir. If R is a field, in R data is field.
Very good question. I was expecting that someone would ask this question. So, see what is left now to check to make R as a field. With addition, we have seen that it's an additive abelian group, and with multiplication, we have seen that it's closure, associativity, identity, commutativity, distributivity is there. So now what remains to show?
Multiplicative inverse.
Yeah, multiplicative inverse. So instead of writing my new question, let me write your question. So this is a question. So maybe Pradeep, I can name this question as your question. It's a very good question. Do you have any problem in that? So if Pradeep asks if R dot is a field, then whether R tilde plus and product is a field. Okay. So what your guess? What do you think? Whether it's going to be field or not?
Minus 1 R has no multiplicative inverse.
Minus 1 R has no multiplicative inverse.
Except that element, all other elements will have multiplicative inverse.
But minus of
The
1 R.
field R star is abelian group. If R is R star, only for R star is abelian group.
Abelian thing we have already checked, right? Commutativity part.
Yes, sir, I have already checked.
Okay. So just inverse property is left, and you are saying that except minus 1 of R, everything has multiplicative inverse with respect to the new multiplication defined. But minus 1 of R is anyway our additive identity, right? So we just need to check for the non-zero elements. And here non-zero element is everything except minus 1 of R. Right? So let X belongs to R tilde minus the set 0 of R tilde, which is the set R tilde minus 1 of R. So whether we need to check that it has a multiplicative inverse or not. So if Y is the multiplicative inverse, of X, then what it need to satisfy? It need to satisfy X product Y. Sorry, is same as is I of R delta, 1 of R delta, and which is same as Y product X. So if we see the first part, then second part will also follow, because we have already seen now that this product is abelian. So yeah, but this will implies X times Y is XY plus X plus Y, and the 1 of R delta is 0 of R, right? And that will imply that X plus identity of R times Y plus X is equal to 0 of R. I'm just taking identity of R common, Y common from XY and Y. Okay. So, and that will imply that X plus identity of 1 of R times Y is minus of X, and that is Y is minus of X, and times the inverse of this element X plus minus R. So this inverse is in R plus dot. Okay, because the calculation we are doing is in R plus dot. So this element I am multiplying both sides with X plus IR inverse, then I will get Y to be minus X times X plus IR inverse. So we just need that X plus IR has to be invertible. Okay, and X plus IR inverse exists for all X in R except when this element is 0. X plus IR is 0 of R. So except this choice, every time this will exist, but this will implies X is minus of 1 of R. Okay. And this is definitely the 0 of R delta. So we have already removed this from our set in consideration. X R delta minus this set. So this is not going to create any problem. So for all non-zero elements, we have an inverse. So 0 of this new set is minus 1 of R. So except this element, every other element has an inverse, and the inverse is minus X times X plus 1 of R inverse. And this inverse is in the original ring setup. So this implies X as multiplicative inverse in this new ring setup. And why this is so? Because we are already choosing our X from this set. Okay. That's why it turns out that R tilde plus dot is a field if the original uh, algebraic structure is a field. Okay. Yeah, any doubt? I must say, Pradeep, it's a very good question. I was expecting that someone would ask it. It's good that you ask. Okay. Yeah, I will just take maybe 3-4. Any doubt?
So you
Yes.
are discussing about R and R delta is isomorphic. You are discussing about R and R delta is isomorphic. Isomorphism.
Yes. R and R delta are isomorphic as ring.
If R is field, it is directly to R delta is field.
Yes. R delta is a ring that we have already checked. Commutative ring with unity. Only thing to check is R delta, all non-zero elements of R delta has multiplicative inverse when R delta has multiplicative inverse. And that follows in, from just by assuming that R is a field. We are not using the isomorphism anywhere. I haven't done anything related to isomorphism in the entire setup. I did calculation just elementary wise calculation I did. I haven't put any isomorphism thing here. So even you can just forget that R and R delta are isomorphic. That's a consequence that we actually got as a second part. But in first part, we proved that it's a commutative ring with unity, right? And after that, it was only left to show that it has multiplicative inverse if R has. So that we did. Okay. Pradeep, satisfied? Do you still have any doubt? If not, then just give me 2 minutes. I will just state one question because that I think is very uh, going to be very helpful for you guys. So, what I want to say. So you have already seen the definition of ring homomorphism, right? There we are used to check 3 properties. So first property was to check that whether they are compatible with the addition phi of x plus y equal to x plus y, and second thing to check is phi of xy is actually xy. Okay. So I am not specifying that this operation is inside R dash and this operation is inside R dash and this is inside multiplication is R dash. That is understood, right? So, and the third property that you use to check that identity is mapped to identity. Okay. But I am saying that instead of checking identity is going to identity, if you check this thing that phi is onto, then that will imply that phi is a ring homomorphism. So what I mean that phi of identity of R will be mapped to identity of R dash if phi is onto and compatible with the addition and multiplication. So if you are checking it something to be isomorphism, and if you have already checked the onto part, then you need not to check that one is mapped to one of R dash. That will always be the case. Okay. And you even I don't think you even need the ring to be commutative. You only need that the ring has unity for sure. So there may be just some lines I will say. So see, to show phi 1 is equal to 1 of R dash. I'm not going to write R and R dash again. You just understood it. Okay. So R dash, it is enough to show that for all y in R dash, y
The conditions
times,
are valid for all x comma y in R.
yeah. This is homomorphism condition. Yes, I should have written here for all x comma y in R. Yes. Okay. Oh. A very silly mistake I did. Yes. Compatibility with the addition and multiplication. So it should be this. Okay. Okay. Thanks, Muthu. So now you got, right? It's just compatibility with addition, compatibility with multiplication, and this is onto condition. So then it will imply that it's a ring homomorphism. So you just need to check that one R is mapped to one of R dash. Okay. So for that, it's enough to show that for all y in R dash, you have y times phi of R dash is same as phi of this y times y. Okay, because that is a condition for uh, something to be just the identity of the codomain, and identity is unique. So if this is satisfied for all I, then we can conclude that phi of 1R is the multiplicative identity of the codomain, right? So for that, since your phi is onto, you have y to be phi of x for some x in R, right? And thus y of phi of 1R is phi of x, phi of 1R, and that is phi of x dot 1R, which is phi of 1R dot x as well. And okay, just so I will do this both the parts simultaneously. So this is same as phi of x, right? Because 1R is identity of the domain ring, and this is going to be y. So this part is satisfied. Phi of 1R y is y, right? If you assume that it's commutative, then it's already done. But if you are not going to don't want to assume that it's commutative, then also we are done, because this is same as 1R dot x. Identity commutes with every element. So this is phi of 1R dot phi of x. Okay. So all these three things are same. Oh, sorry. One more step I have to write that. So this is going to be phi of 1R dot y. Okay. So this element is same as y and this is also same as phi 1r dot y. And I'm not using the commutative part, so this is true for any ring. This will all implies that phi is a ring homomorphism. Now, one question that should come to your mind immediately, that whether the converse is true. If we have this thing, then whether always we have the onto condition. If that would be the case, then what's the need to define phi of 1r to be 1r dash? Why? What's the need to define homomorphism like this? We should have said that homomorphism is just an onto map which is compatible with addition and multiplication. Okay, but actually the converse is not true, and you can just see a very trivial example. So converse is not true. So these kind of questions sometimes you may find in some competitive exams also, that this might be the two statements you might need to check that whether these statements are true or not. That compatibility with addition and multiplication with onto implies that it's a ring homomorphism, but the converse part is not true. The converse is not true because you can just see this map. Phi from the ring of integers to the ring of rational numbers, even it's a field. So mapping just n to n. So you can easily check phi is, so you can check that phi is a ring homomorphism. Phi is a ring homomorphism, but phi is not onto. Okay. Yeah, so I thought that this might be helpful for you, because if you are checking a ring isomorphism, that it's enough to check onto part. Instead, this will give you automatically this phi of 1r is 1 of r dash. So you need not to check phi of 1r equal to 1 of r dash and you check onto separately. Just check onto, it will do for both. Okay. Yes. So with that, I would stop here. If there are any questions, any doubts, anything, then you are welcome to ask. Okay. So if there are no questions, then maybe I can stop here.